So if we have a rectilinear point, 5 square root of 3 minus 5, the radius is easy, right? We just plug it into the radius formula. So it's going to be 5 square root of 3 squared. Negative signs almost never matter for finding the radius, because when I square it, we're going to get rid of that minus sign. So what does that equal? So 5 square root of 3. Common mistakes that you will do, just be careful not to like double square the square root of 3. So it'll be 5 squared, which is 25, and then square root of 3 squared just makes it regular 3. Easy kind of brain flub to make that a 9 or something. Then plus 25. And so what do we get? So 75 plus 25 is 100. And this is r squared. So r, just 10. You can always use the positive square root. And actually, so the points I put on where you got to convert from rectilinear to polar and vice versa, I will always use just by a standard of r is positive and our theta is between 0 and 2 pi. Doesn't have to be, but for me, it's just I don't see a reason to extend beyond there, other than kind of just challenging you with more math. But if you can understand that much, you're good, in my opinion. So always use a positive radius. And now we just need to find theta. So we'll get tangent of theta is y over x. We got to keep track of the minus sign. And so, of course, we get negative 1 over square root of 3. And again, it just matters remembering your pre-calc and all your trig from that. Pre-calc, I always tell my students, here, let's draw them to scale. You need to know 2 triangles. There's the 45, 45, 90, which has ratios of 1, 1, square root of 2, and then the 30, 60, 90. 30, 60, 90, the way you remember it, short side's 1, hypotenuse is the long side's 2, other side square root of 3. Pretty easy to remember those numbers. 1, 2, 3. 1, 2, square root of 3. And then 1, 1, square root of 2. And then, of course, the short angle, pi over 6. Bigger angle, pi over 3. And so if we need a tangent whose ratio is 1 out of square root of 3, I'm going to have my theta, my reference angle, pi over 6, and we just have to decide what quadrant we're in. So the reference angle is a reference angle of pi over 6, since that will give me a tangent ratio of 1 over square root of 3. Since it's negative, you just have to decide, well, what quadrant are we in? We are in the 4th quadrant. X is positive, Y is negative. And so our reference angle is a pi over 6 reference angle. Our reference angles are always drawn from the x-axis, positive or negative. And so we're given that, essentially that's my angle right there. And so that'll give me a point. I'm going down on the y of negative 1, and then my x will be positive square root of 3. Hypotenuse is always positive. So I'm just redrawing this triangle now in its reference position. And so what should our theta be in this case? The theta we can count. So now I got to actually measure the actual theta. And it's always measured from the positive x-axis. So we can either go all the way around, or we could go negative if you like. You could throw in a negative pi over 6 just to be quick and easy about it. Since we're just going down pi over 6, it would be a negative. Of course, if you want to restrict between 0 and 2 pi, not necessary. But again, it's a multiple choice test, and I put all the answers following this. So what is a negative pi over 6? Instead, if I go all the way around, well, if I go all the way around the circle, it's 2 pi, which is 12 pi over 6. But then I got to go back pi over 6. So 11 pi over 6. So if you forget your trig. That's how I do it. That's how I kind of count things. Useful information. Pi is, the denominators are always pi over 2, pi over 3, pi over 4, or pi over 6, right? So pi is 2 pi over 2, 3 pi over 3, 4 pi over 4, 6 pi over 6. Right? Easy. All you guys should know this by Calc 2. Maybe no one's just kind of pointed that this is a very useful way of thinking about it. Do the same thing with 2 pi, 4 pi over 2, 6 pi over 3, 8 pi over 4, 12 pi over 6. So if you need to review, or if you need to figure out an angle, you can always figure out your reference angle just by these basic triangles. Whatever the ratio is, if you're trying to solve a tangent of theta, or even if it's like cosine of theta, if you're looking for cosine of theta equal to -1/2, and you want to solve that equation, your ratio is 1 over 2. Negatives don't really matter at the sort of the first pass, and you're just looking for what angle has a cosine of 1 over 2. So you go up to your two reference triangles. Pi over 3 is your reference angle. What quadrants do you need to be in? It's negative, so we need quadrant 2 and 3. And so now we're looking for a pi over 3 angle in quadrants 2 and 3. Sorry, let me draw that again to make it more to scale. So there's one in quadrant 2, and then the other angle will be pi over 3 with the negative x-axis. Those are your two solutions. Now you just need to find the actual angles. And how do you do that? Well, if I go pi, my denominator is 3, so pi is 3 pi over 3. How do I go get this angle? Well, I go 3 pi over 3 and then go back 1. So if I go 3 pi over 3 and back 1, I'm at 2 pi over 3. How do I get to this angle, the furthest one? Well, I go pi over 3, so 3 pi over 3, and then 1 more pi over 3. And those are the two solutions to our cosine theta is 1/2. So give yourself a refresher on the trig. That's kind of going to be the hardest part. Otherwise, it's just plugging things in the formulas. If I give you the x and y, you can find r easily. The tangent theta is something where you got to do a little bit of trig. If I give you r and theta, plug them straight into these formulas. Again, you just have to then remember what is sine of that angle, what is cosine of that angle. But more things we need to do with trig equations. Practice graphing these. Again, it's hard to build an intuition for these. It takes a little while to get used to graphing, and unfortunately, you don't have a little while. You've got to really try to master it in the next 3 or 4 days. Because we need to do calculus now. So we need to do tangent lines. Tangent lines are essentially the same as they are with parametric equations. You can really think of polar coordinates as a parametrization in some sense. Whenever I'm given a polar function, r in terms of theta, it gives us a natural parameterization of x and y. So for example, let me find my example. If we have r is 1 plus sine theta, and we want to find the slope of the tangent line when Theta is pi over 3. Well, just like we did in parametric plots, our tangent line, of course, the slope of the tangent line is given by dy dx. And, well, our parameterization now essentially is going to be theta, because r is specifically in terms of theta. So kind of generically, at least in terms of our chain rule, we can write it as dy d theta over dx d theta. Just like we did when I had x in terms of t and y in terms of t. Well, so why do I get these? How do I get dy d theta and dx d theta? We go back to our defining equations, or defining transformation from polar to rectilinear. We have x is r sine theta and y is r, backwards those. Ugh. X is r cosine theta and
Thank
y
you.
is,
You actually made a mistake before.
what'd
I
you
was
say?
going to check that.
Did I write those down? Oh, I did write those down backwards. Apparently I'm dyslexic today. Yeah, so those should be switched. R cosine theta for x and r sine theta for y. And y is r sine theta. So, well, if r is a function of theta, then I can essentially stick in this 1 plus sine theta in for my r's. And then I have x parametrized by theta. I have both functions of x and y, or x and y are both functions of now just one variable, theta. And so this is, you can essentially think of the theta as a t if we wanted to change the variable, right? Nothing would really change. And we essentially have that same chain rule. So we just compute them. So let's distribute that out just to make our lives a little easier. We'll have cosine theta plus sine theta cosine theta. Looks like x will have a chain rule here, or product rule, excuse me. Y, we'll just get sine theta plus sine squared theta. That should be a pretty easy derivative. My dx d theta is going to be negative sine plus, let's see, sine theta minus sine theta plus cosine theta cosine theta. So simplifying, we got negative sine theta minus sine squared theta plus cosine squared theta. My dy d theta is going to be cosine theta plus 2 sine theta cosine theta. So conceptually, hopefully not too bad. We just have more work to do now in some sense, kind of like we've been saying with these parametric equations. It's a lot of the same calculus. We want to take derivatives, and then we just got to take ratios of derivatives. And so because we have two derivatives to take, a little bit more work. Now I got to compute the ratio. One thing I'm going to do to kind of shorten our work, we don't just need dy dx for all theta. We only need it for one theta. So even before computing a ratio or trying to simplify or anything like that, we can go ahead and plug in the theta for both dx d theta and dy d theta, and then get pure numbers for that, which will help simplify our calculations when I have to divide them. So our dx d theta evaluated at pi over 3. What do we get? So we get minus sine of pi over 3. And again, always keep your reference triangles handy. Pi over 3 is the bigger one. Our ratio is 1, 2, square root of 3. Sine is root 3 over 2. minus square root of 3 over 2 squared plus cosine is then going to be 1 over 2 plus 1/2 squared. And let's see, can we simplify this much? So it looks like we've got negative square root of, let's write it as negative 2 square root of 3 over 4, since our denominators here are going to be 4, minus 3/4 plus 1/4. And so it looks like we've got negative 2 minus 2 so minus 2 square root of 3 over 4 for our dx d theta. Hopefully the dy d thetas, usually the denominators work out the same, which is kind of nice because when we take the ratio, those will just cancel and save ourselves a little bit of algebra and arithmetic. So cosine of theta was 1/2 plus 2 times square root of 3 over 2 times 1/2. And actually, it looks like this one we could simplify with a denominator of 2. But let's go ahead and keep that 2 in there and keep the denominator as 4 just to keep them matching. So we'll have 2/4 plus 2 square root of 3 all over 4. So I've got my dx d theta, my dy d theta, evaluated at the point we care about, pi over 3. And then we just take the ratio. So my dy dx is going to be equal to 2 plus 2 square root of 3 over 4 divided by minus 2 square root of 3 over 4. Simplifying, when I take that reciprocal, we'll have 2 plus 2 square root of 3 over negative 2 minus 2 square root of 3. Any other simplifications we can make?
Take the -1 out of the denominator.
Good. And so the whole numerator and the whole denominator cancel, and we are left with just -1. So try to look for those simplifications if you can. Obviously, -1 looks way nicer than that. May not always work out that nicely. I mean, you're commonly going to see these square roots of 2 and square roots of 3. If you can remember doing any trig stuff, right? Those are the ratios of the triangles of our two triangles have these square roots of 2 and square roots of 3 commonly in them. So you don't have to rationalize the denominators. If it ends up not simplifying, I would say, like, if this was -2 plus 2 square root of 3, then we can't really divide and simplify things. Do be careful, though, with the way we factor this. You know, don't cancel just the square root of 3s or anything like that if the signs don't match up. You do have to factor completely. So this is our slope, the part B of this question. Other things we could ask are things like find vertical tangent lines or horizontal tangent lines. These ones are actually a bit simpler in some ways, a little more complicated in other ways, I guess. So what were our vertical tangent lines? Think of this, again, just as a parameterization. I have y and x parameterized by some function of theta. So x of theta was cosine plus sine cosine. And my y as a function of theta was sine plus sine squared. Well, when do we have vertical tangent lines? Vertical tangent lines, again, just as with our parameterization case, if we were parameterized by t, are when dy d theta is 0, right? A vertical tangent line, oh, sorry, dx d theta. I'm drawing it and getting my geometry backwards today. If my x-coordinate is not changing at all, I'm just going vertically. I can only go vertically. So our vertical tangent lines, our dx d theta is 0. We just take our dx d theta and solve that equation. So dx d theta we had as minus sine theta minus sine squared plus cosine squared theta. We set that equal to 0. So this was in the book. So let's see if we can solve this. We should be able to. Might not be able to. Of course, we want to be able to solve it. This is the method. Vertical tangent lines, dx d theta equals 0. Horizontal tangent lines, dy d theta, we set equal to 0. We do have some messy derivatives, so how can we solve that? It might be easiest to convert the sines to cosines. We could use a double angle formula, right? If I factor out a negative, I'll get cosine squared minus sine squared, which is cosine of theta, cosine of 2 theta. But cosine of 2 theta and sine of theta, figuring out where those guys are equal is going to be hard. I don't know if you can do that by hand. So we just kind of got to go through the gamut of all of our trig problem solving techniques. It's often best if we convert all of the units or all of the trig functions to one trig function. So let's actually convert the cosines to sines and see if that helps us. So plus 1 minus sine squared theta equals 0. And so that gives us 1 minus sine theta minus 2 sine squared of theta. And this looks like a little bit better. So common things you want to look for in these types of trig equations, see if you can factor. Sometimes you can factor out if there's a common factor of sine, maybe you can factor them in nice ways. And then once you've factored, always look for things like sine squared plus cosine squared. You can reduce the Pythagorean identity. Unfortunately, the signs don't match up in this case. So you could use a double angle identity, but I would say avoid using those because they're harder to solve. You ideally want all of the angles to match. So theta, 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 instead of like having sine thetas and then like cosines of 2 thetas, get really hard to solve. And then of course the other technique I was thinking of is when in doubt, try to convert things all in one trig function. So if you convert all your cosines to sines, 1 minus sine squared, now it's just a nice quadratic in sine squared. So does that factor? I think it should, right? So we will have 2 sine squared. Let's, we can write it. So we'll have 1 and 1. I will have a minus 2 sine theta and a plus sine theta. Everyone catch that? So foiling, for me, some of these, you just get in the habit of guessing and checking, right? Of course, the factors of 1 are 1 and 1. The factors of 2 are 2 and 1. And since it's a negative, it's essentially the only thing can it be. Let's double check, make sure it works out. Minus 2 sine times sine gives me that minus 2 sine squared. Of course, a minus 2 sine plus a sine gives me that minus sine. And of course, 1 times 1 gives me 1. So easily factorable. And then we just solve from there. So set each one equal to 0. So sine theta is -1, sine theta is 1/2, and then you just pull up your reference trig angles. This is all kind of back to pre-calc. Sine of theta, when is sine of theta 1/2? So we need sine, so 1/2 will give me a pi/6 reference angle. Since it's a positive 1/2, everything is positive in the first quadrant. So I will have that exact reference angle. And then sine is also positive in the second quadrant. So you can draw it somewhere. We need a second quadrant pi/6 reference angle. So 6 pi/6 minus pi/6. We get 5 pi/6. And of course, since we can wrap around the circle, you can add your 2 pi n's there. Likewise, we want to do the same thing for -1. Whenever sine theta, cosine theta is -1 or +1, you kind of just have to remember those. So of course, sine is -1 at 3 pi/2, and then I can wrap around the circle 2 pi n times. So at any of these angles, we will have vertical tangent lines. And of course, if we were asked, theta, if we restrict our theta between 0 and 2 pi, we can get rid of the 2 pi n's. Essentially, when our theta, as we move around, pi/6, it'll be vertical, 5 pi/6, it'll be vertical, and then 3 pi/2 will again be vertical. Horizontal, we want to do the same thing. So our dy dx was cosine theta plus 2 sine theta cosine theta. So excuse me, dy d theta. When our change in y is 0, we got to be horizontal. So this will give me where the horizontal tangent lines are. And again, go through your gamut of pre-calc trig problem solving. In this case, it looks like we have a common factor. There's no squareds, so we're not going to be able to use any sort of trig identities. Probably can't convert them all into sines or cosines, but luckily, as it's written, it factors. You can factor out a cosine theta times 1 plus 2 sine theta equals 0. And since it factors right off the bat, I can just set each factor equal to 0. Cosine of theta is 0 at pi/2, 3 pi/2, and continuing. So this one's actually a cycle of pi m. And this one, of course, we get sine theta equals -1/2. So our reference angle is pi/6 again. But since it's negative, we need the third and fourth quadrant. So draw it out if you need to. We'll have a pi/6 here and a pi/6 there. So what's our theta? Our theta is 6 pi/6 plus 1 more. Gives me 7 pi/6. And then I can go 12 pi/6 all the way around, and then back 1 gives me 11 pi/6. And all of those will repeat periodically every 2 pi. And so those are the angles where we have horizontal tangent lines. Any questions on that? If you need to find the equation of the tangent line, what would you do? Let's go back to the first part. So we found, they give us a point, and they say theta is pi over 3. Find the slope of the tangent line. So we found both the derivatives, dy d theta and dx d theta. We took their ratio to find dy dx at pi over 3. And what did we get? We got -1, right? So how would we find the equation of the tangent line? We do just like we do in parametrizations. We have our slope. We need to find our point. So we would go back our x at pi over 3. We had x as cosine theta plus sine theta cosine theta. So we need to find our point. We plug in our theta of pi over 3 into our x and y equations. Cosine of pi over 3 is 1/2. So sine is going to be square root of 3 over 2. And so it looks like we're getting 2 plus square root of 3 over 4 is the x coordinate. And our y at pi over 3 is going to be sine plus sine squared of pi over 3. So we'll have square root of 3 over 2 plus square root of 3 over 2 squared. And so simplifying, that's going to be 3/4. So it's going to be 3 plus 2 square root of 3 over 4. So that'll be our 3/4 plus, and multiply that by 2 over 2, 2 square root of 3 over 4. Gives me my x and my y. And the equation of a line, of course, because we have these square roots, it's going to look complicated, but just mind your parentheses. We just put it all in slope-intercept form, so it'll be y minus that number, 3 plus 2 square root of 3 over 4 equals -1. I don't even have enough space to write it. Let's put it on a different page. So we have y minus 3 plus 2 square root of 3 over 4, whole quantity, equals -1, x minus, and our x coordinate was 2 plus square root of 3 over 4. And then if you want, now it's just arithmetic. So we'll distribute the minus sign, minus x plus 2 plus square root of 3 over 4. If I add that whole guy over, it'll become positive. So plus 3 times 2 square root of 3 over 4. And what do we get? Minus x. Looks like I've got plus 5 plus 3. So 5 raw numbers plus 3 square root of 3 all over 4. And that's the equation of our line. Of course, the other thing we might want to do is then convert this to some sort of polar equation. If we want a polar equation of a line, how do we solve for it? We just replace our x and y with their respective sines and cosines. And now in this case, we would factor out our r. So if I add this over, we have r sine plus cosine is equal to, so I subtract or added that guy over. On the right, we've just got our 5 plus 3 square root of 3 over 4. So our equation is r is equal to 5 plus 3 square root of 3 over 4 sine theta plus cosine theta. Gives us the polar equation of a line. So I'm not sure how much of this kind of stuff you guys will have to do. I'm sure you'll have to find the tangent lines, at least finding the slopes like we did. Finding these equations, it's just kind of like extra work. Hopefully you guys are all pretty much experts now at point slope form of line, right? There's just kind of more work to do. None of it was really calculus. We just had to plug in the theta to find our x point, plug in the theta to find our y point, plug that all in the slope intercept, and then do the algebra. A little bit of new stuff here if we want an actual polar equation of the line. But again, that's just extra practice from converting from a rectilinear equation to a polar equation. Any questions? So that is good stuff to practice. Other than converting points, you have to convert 1 point from polar to rectilinear, 1 point from rectilinear to polar, and then I think you have to convert a polar equation to a linear equation. So given a polar equation, if I was given something like this and had to convert back, again, just use those 4 defining equations. Our r is going to be square root of x squared plus y squared. And then my sine theta and cosine theta, you can solve for cosine theta is x over r, and then replace r with square root of x squared plus y squared. It's all just a matter of manipulating those equations and then doing the algebra. Any questions on tangent lines, slopes? Because the next thing we want to get into is areas. Areas is a little more complicated because you got to really understand the graphs of polar coordinates, and it's easy to just misthink things if your brain isn't thinking in polar coordinates in these rotational graphs. So let's start off with one that we've seen. Let's see, do we have one that we've seen? Well, let's start off with graphing one. Let's do a fairly easy graph of r is equal to square root of theta. So what's that going to be? It's essentially saying we can plug in our theta and make our table again. When theta is 0, what's r? 0. And what's going to happen as theta increases, so my theta is pointing in this direction, and then theta is going to rotate. And as theta increases, my r is going to increase. So it's going to look like this. It's going to be a spiral. And you can kind of see that, right? If we pick points, our theta is 0, we'll get 0. Our theta is pi over 2. R is just square root of pi over 2. Which means, so this point here, the radius, square root of pi over 2, pi over 2. What happens when theta is pi? Of course, r is square root of pi. So as theta rotates around and we're over here at an angle of pi, the distance is square root of pi. So r is going to keep increasing as theta increases. And of course, if we kept wrapping around, it would keep increasing. Here I've gone all the way around the circle, so my angle is 2 pi, which means the radius is square root of that. Oop, square root on that one. And now let's suppose we want to find the area that is enclosed by this conch shell looking thing. So what we want to do in our typical calculus fashion, if we kind of blow up that one piece, let's just blow up this first piece. Normally with our graphs, we cut up the x-axis and because we have y as a function of x. So we make our vertical parts f of x, that the height we can compute by knowing the x value. In this case, we have to cut things up radially because our r is a function of that angle. So you want to think of slicing things like you would a piece of cake or a pie or a pizza. And we have some now angle here that we're slicing, which we can call our d theta. And we want to approximate the area of this guy. So how do we get the area? Again, you got to remember all your circle stuff from pre-calc. Our area and our sector equations. What's the area of a circle? 1/2 pi r squared. And that essentially pi becomes the, it's essentially half the theta, half the angle times r squared. Sorry, I think I said the wrong thing. So what is the area of a circle? Pi r squared. And so in a full circle, we go all the way around. It is that 1/2 of the full angle that we traverse. And so really the area of a circle just comes about the area of a sector. Namely, if I had a nice complete circle, the area of a piece of pie is given by this equation, where our theta is our subtended angle. Well, this one's not an exact circle. Again, it's a spiral, and the radius is going to be gradually increasing. But in our approximations, this is essentially what we're doing in some sense as our Riemann sum, where I'm breaking down this segment and maybe I can approximate it really closely with a circular arc. And then on each segment, we do that exact thing. And I approximate the area. Yeah, in this case, we're going to be an overshot. We could also approximate it with maybe the outer Riemann sums and make our arcs this way. Just as with normal functions, we have right-hand Riemann sums, left-hand Riemann sums, trapezoidal rule, Simpson's rule, and all that. The key point is I can at least approximate the area with these slices of 1/2 r squared theta. And actually what we would have then is that our area differential is going to be 1/2 r squared times the small angle in that. So of course, each of these slices then is going to be like a dA. And then what do we have to do? We add all those up. And the finer and finer partitions we take of our theta, the more we cut up the circle, or at least our angles that we're traversing as we go around, the closer and closer these approximations are going to be. And so this is our defining formula for area. What's the key difference? In rectilinear, well, we're using squares and rectangles. So our area differential was just the base times the height. And the height is just given by y. And so now we just have to be careful, because look, in our area differential here, we have extra constants coming out as well as an r squared. So whereas here, if I have y as a function of x, I just have my area as f of x dx, and then we integrate both sides to find the area. That's what we've been doing all year. In this case, we got to remember this 1/2 and to square the function. So our area is going to be 1/2 whatever the function is. So if we have r as, let's say, g of theta, we'll have a g of theta squared d theta. So this is our formula. Another one that's going to be good to remember, good to memorize for areas in polar coordinates. Let's go back to our example now. So our function now, r is square root of theta. What are the bounds for theta? In this case, they would have been given, since we want a definite starting and ending point. So we'll go from 0 to 2 pi. And we set up our integral following our formula, now with just definite bounds. So our integral from 0 to 2 pi, we have 1/2 square root of theta is our function, squared d theta. And so what do we get? Of course, squaring that, we'll just get a 1/2 theta, d theta. So we get 1/4 theta squared, and we got to evaluate between 0 and 2 pi. And when we plug in 0, we'll get 0. So we'll get 4 pi squared over 4. Total area is then pi squared. Any questions? Anyone still writing on that? So let's do a few more examples, because these can get a little tricky. And so we'll just kind of increase our level of difficulty as we go on. The easiest one is when I give you a function, r as a function of theta, and say, find the area under this curve from some definite bounds. And when I say under the curve, we mean radially. And so what do we mean by under the curve? It's really inside the curve. So from the curve towards the x, or towards the origin, is how you're filling in these areas. So I could say things like, find the area under one loop of the clover r is equal to cosine of 2 theta. Have we graphed this yet? Have you guys tried to graph this guy? We've done r is equal to cosine theta, and I think r equals sine theta as well. or at least one of those. 2 theta, things get a little tricky. Let's go through it real quick, just to practice graphing. So I make my step, again, pi over 4. At 0, cosine of 0 is 1. Pi over 4, when I multiply it by 2, I'll get cosine of pi over 2, which is 0. So from here, my angle, remember, is 45 degrees. When we rotate upward, I'm rotating this point upward, but by the time I get to 45 degrees, I should actually be at 0. So the radius is going to be decreasing and coming down to this point here at 0. Pi over 2, I get cosine of pi. So our pi over 2, I'm pointing straight up. But what is cosine of pi is -1. So if I'm pointing straight up, but then have a negative radius, we're down here at -1. So the graph, we came over, we're going to pass through the origin at a 45-degree angle. And then we are going again, we're going to increase and then come down here to -1. And we keep going with this. What happens when I plug in 3 pi over 4? Because of that 2, it'll make it 3 pi over 2, and I'll go back to 0. So 3 pi over 4 is pointing this way. But the problem is our r is going to be negative. So even though I'm pointing this way, I'm coming in from the negative side. So if you can kind of think, we were at pi over 2, which was vertical, and I'm now at a negative radius. The radius is going to be negative and then slowly increase as the angle rotates around. So we're going to come back up this way and then pass through the origin again at a 45-degree angle, pointing in that 3 pi over 4 direction. And then at pi, we'll have cosine of 2 pi, which is 1. Going to be a little weird again, though. Radius is 1, but my angle now I'm pointing at pi. And so we will be here. So it'll come around and then pass through that point. That's essentially the first half. If you would continue this, it's going to keep that same pattern going. So it'll come, pass through 45 degrees, come up, hit a peak, and then come down, pass through 45 degrees, and then go out to that rightmost peak. And it looks like this 4-leaf clover. And so we want to find the area of one petal. Just a heads up as well, I know you guys use Desmos a lot. We're in a weird spot in terms of our educational system, I think, just because we're in such a digital age, right? And we want you guys to use technology, but then we also don't want you guys to use technology, and it's just weird. And so I think we're still in the process of kind of re-changing our educational system. I think we need to actually just make more use of it since everyone's using these digital stuff anyway. Unfortunately, it's hard to kind of test over that. Let me change my graph. So there was one graph. If you're using Desmos, I think it's over here on the right if you want to do polar coordinates. Let me move the zoom thing out of the way. You click on the little graph settings. And so typically we're in the rectilinear grid. And if you click on this guy, it gives you a polar grid. You guys can all see this, right? Graph. And then you can always keep it in radians unless we specify degrees. And then let's close that. You can always type in the function over here. So r is equal to, what do we have? Cosine of 2 theta. And it gives you a nice, you can see the graph there. I think one of the problems of Desmos is, I don't know if someone knows anything more about it. They have examples over here on all these graphs. And I don't know if I need to like sign up for an account or get a professional account or something, but I was trying to having some difficulty recreating some of these. Here's one with like a rose petal and a natural polar coordinates. And they give you like an A over B, and then they give you this slide ruler where you can change the value of your A and B. It would be helpful if there's some sort of way to trace the curve. And I don't know if there's some way to do that, or if any of you guys know. It might be something worth playing around with. Let's close this and go back to our other graph. We got R is cosine of 2 theta. Helpful for checking your work. I would say you really want to try to practice these by hand, because if you get too used to technology babying you through it, you're never going to develop the skills yourself of understanding why is this the graph of cosine of 2 theta. I would really say, try to do it yourself, because there is some practice in being able to understand, well, how this curve is traced out as theta increases and what's really causing this shape to come about. Good check, of course, it'll be a much better drawing and much better visualization once you get it, but practice them by hand, maybe play around, see if there is some sort of trace setting on that. Okay, so let's go back to the paper. So how do we find our area of our petals? Well, the area is still going to follow this formula, 1/2 r squared d theta. And so we will have 1/2 cosine squared of 2 theta d theta. But now we have a little bit of work to do, because what are the bounds? One note is that the bounds need to be continuous. i.e. consecutive. So of course, even as my theta increases, I started here at 0, and we loop around. Where were we at 2 pi? We were here. We were at pi. And then it took us 2 pi to go all the way around. Back. So every 2 pi, it's going to keep repeating. And our problem is I don't want to start at 0, because if I start at 0, what happens after I reach this point? I don't continue on in this petal. I can't integrate from like 0 to pi. And I don't want to do like, you could if you wanted to split it, but you would have to integrate from 0 to pi over 4, which would give us this point. And then continue on, go all the way around. And then back here at 5 pi over 4 to 2 pi. Not going to be the best way. The best way is actually, well, we want to figure out where we are, or where are we at this origin. So we're going to be at the origin, pi over 4, 3 pi over 4, any sort of odd multiple of pi over 4, we're going to be at the origin. But what do we also need? We want to be pointing between those two angles. So this is our pi over 4 angle. And this angle is 5 pi over 4. But again, those aren't consecutive. I have to skip a bunch to go from pi over 4 to 5 pi over 4. This is what I mean by like continuous and consecutive. We need to go around in the correct order of theta. And so it would actually be helpful, maybe if I started down here, as theta increases, I'm going up to this angle. So a better angle might be minus pi over 4. You have to use your trigonometry, your repetitiveness, the periodicity of the circle sometimes to make it the correct choice of angle, to make sure that it flows in the right direction from the area you want to start with and then the area or the ending area, so that you're not counting extra loops by going around this way. So our integral minus pi over 4 to pi over 4 of our function here. So we had 1/2 cosine squared 2 theta d theta. We could have started at 5 pi over 4 and continued if we wanted to. If I know that I'm at this angle, I'm traveling on this part of the pedal, 5 pi over 4. But we would have just had to continue on beyond. It would have been 5 pi over 4 to pi over, or to 2 pi, and then to up here would be 9 pi over 4. So you could also do 5 pi over 4 to 9 pi over 4 if you wanted. By the periodic nature, should give us the same answer. And the way you want to think about it, again, I didn't draw the lines on this, the shading right. If we're starting here, I am essentially calculating the area as my particle moves around in the angle increasing. I don't know if you guys can see this. I'll try to get my hand out of the way. We're counting the area from the curve to the origin. So you can essentially imagine it filling in as we go across this way. And our problem is, right, if I had started at this pi over 4 and continued, well, now I'm starting to fill in this area on the other pedal. So we don't want to go that way. Does that make sense? Oh, we've gone over. I got to give you guys time for the quiz. Almost forgot about that. So that's it for areas. We will talk more about this tomorrow. Let me adjust the quiz here for you guys, since I kind of wasted 15 minutes here of your time. I did want to get through some of those integrals. And tomorrow we'll have to continue with this. It'll be a little bit more complicated, because more things we have to do with integrals are finding the areas between curves. And that gets a little tricky.